This section deals with applications of determinants, and so we're going to see how you can use determinants to find solutions to linear systems, as well as the inverse of matrices. Cramer's rule is a technique that can be used to solve the matrix equation AX equal to B, and all you have to do is to find any value xi, given here. You take the determinant of AIB and divide it by the determinant of A. So all we need to know is, what is AIB? A, of course, is the coefficient matrix in our linear system AX equal to B. So AIB is the matrix that you get when you take the matrix A and replace the ith column with the vector B. So for example, if we wanted x1, then we'd have x1 is equal to the determinant of A1B. That means B would replace the first column of A divided by the determinant of A. Just to clarify before we start working this problem, Cramer's rule can only be used for cases where you have an n by n matrix that is invertible. So if the matrix A is not invertible, that is, the determinant of A is equal to 0, then you cannot use this technique. Right, so we're going to solve this linear system using Cramer's rule. So here you see the matrix A, and you can show on your own that the determinant of A is equal to 6. So to find x1, which is given here, we have to take the determinant of A1B and divide it by the determinant of A. So we found the determinant of A. Now we need to think about what A1B is. So here is the matrix A1B. Notice that A1B is the same thing as the matrix A, except that the first column of A has been replaced with the vector B. You can show on your own that the determinant of A1B is equal to 13. So now we know that x1 is the determinant of A1B, which is 13, divided by the determinant of 6. To find x2 in our solution, we need to find A2B, or the determinant of A2B divided by the determinant of A. So A2B is simply, again, the matrix A, but in A we've replaced now the second column of A with the vector B. If you find the determinant of A2B, then you'll find that the value is -6. So now we know that x2 is equal to the determinant of A2B, which is -6, divided by the determinant of A, which gives us an answer of -1. To get x3, we need the determinant of A3B divided by the determinant of A. So A3B is the matrix A, where the third column of A has been replaced with the vector B. Finding the determinant of A3B, we find that the answer is -3. Therefore, x3 is equal to the determinant of A3B, which is -3, divided by the determinant of A, which is 6. So for x3 we get an answer of -1/2. Finally, we have our solution, and we can write that as a vector, x equal to 13/6 minus 1 minus 1/2. Here's an attempt to show how Cramer's rule actually works. So first, let's let the identity matrix sub I of x be the matrix with the ith column of the identity replaced with x. So for example, if I had I1 of x, and I replace the first column of the identity matrix with the vector x. So if you look at what's to follow right here, you see that we have A times I subscript I of x is equal to A times, and this is a matrix where E1, E2 just represent the columns of the identity matrix, and the ith column is replaced with x. So that would be EI, for example. So now we just alter the expression by taking the product of A with the identity, and we get the following. So notice that this thing that says A times x, if we have the equation AX equal to B, then we can replace A times x with B. Likewise, if I take the product of E1 with the matrix A, then what I get is the first column of A. So I can replace AE1 with A1, which represents the first column of A, and AE2 with A2, which represents the second column of A. So we now have the following matrix right here. And notice that this is simply the matrix A with the ith column of A replaced with the vector B. So now we're almost done. We simply find the determinant of the left-hand side and the right-hand side respectively, and then use properties of determinants to separate the product of the determinant of the product equal to the product of the determinants. And so all I really need to do to convince you that we're finished is to show that if I take I subscript I of x, it's the same thing as the element xi. So I actually want you to think a little bit about why this statement is true, and that is that I subscript I of x is equal to xi. Of course, from here, if we solve for xi, then we end up obtaining Cramer's rule, which is given here. Just one more note about Cramer's rule, and that is, although this is nice and all you have to do to find the solution to a linear system is to find determinants, it becomes very ugly if you have to do this for a very large matrix. So you would not want to use Cramer's rule if you're dealing with a large matrix equation. Now we're going to investigate a method for finding the inverse of a matrix, again using determinants. The inverse of A, again A must be invertible, is the adjoint divided by the determinant of A. All the adjoint is the transpose of the matrix of cofactors of A. So if you recall, the cofactors of A, which are known as Cij, contain the sign times the determinant of the matrix that you get when you remove the ith and jth column of A. So the adjoint of A, which you see here, is the matrix of cofactors, which we have here, and then we simply take the transpose of that, which gives us this right here. And of course, this is for the 2 by 2 case, but any other case would work the same way. You find the cofactors, you find their transpose, and that gives you the adjoint. Now we're going to use the adjoint to find the inverse of this 2 by 2 matrix. So recall that the cofactors are given by this, and we have to find the adjoint, or the determinant of the adjoint of A divided by the determinant of A. So first, the determinant of A is given by minus 1 times 3 minus 4 times 2. So we get minus 3 minus 8, which gives us an answer of minus 11. Right, so now let's look at C11. Right, so C11 says it's minus 1 to the 1 plus 1. So really all you're doing is you're doing the plus minus that Ms. Wilson showed you on the last video. Sorry, this one should be minus. And this one is minus and the other one is plus. Alright, so for C11 we start with the positive element, so it's going to be plus the adjoint, or the determinant of A11, which is eliminate the first row and the first column, and we end up with the value 3. To get C12, I go to the first row, second column, which is this element, which notice has a negative sign, so it's minus, and then I eliminate the row and the column associated with that element, and I'm left with 4. So the adjoint is the matrix of cofactors, and we take its transpose. So we end up with the matrix 3, -2, -4, -1. And so now we know that the inverse of A is the adjoint divided by the determinant. So we have minus 1 over 11 times the adjoint, which is 3, -2, -4, -1, which gives us a final answer of -3 over 11, -2 over 11, those numbers, this should be a positive, and this should be positive. So we have 4 over 11 and 1 over 11. So that is A inverse. So at this point I would like you to pause the slides, well this is actually the end, and find the adjoint, or find the inverse of this 3 by 3 matrix using the adjoint. And you should turn that in for your assignment on Wednesday.